Okay, so today's notes are going to be on properties of real numbers, and our content objective is going to be to graph and order real numbers and identify properties of real numbers. It's going to be great stuff. So our language objective is going to be to use the correct vocabulary when discussing specific sets of real numbers and the properties of real numbers. So I'm going to jump into the rest of the notes, but if you need to pause and write down these objectives, or for more time to write down these objectives, please do so. But I'm going to jump right in by making a Venn diagram showing us or breaking down the sets of real numbers. So I'm going to make kind of a large box, and this box is going to represent all real numbers. So real numbers are any numbers you've probably worked with before. There are such things as imaginary numbers, believe it or not, but we have probably not used them at this point. We might use them at some point this year, but don't worry too much about them. The vast majority of the time, and for most math you will ever do, you will be working with real numbers. So real numbers is really just any number. And the first thing we're going to do is break up or talk about the two different types of real numbers you can have. And those are rational numbers and conversely irrational numbers. So rational numbers are, again, the most common numbers we work with. So these are anything from fractions. So some examples could be 1/4. It could be any repeating or ending decimals. So you could have 0.1 repeating, or you could have 0.15, or you could have any just normal whole number or negative whole number or fraction. So -3, all of those are examples of rational numbers. The easiest way to understand them or compare them is by looking at irrational numbers. So irrational numbers are numbers like pi, or the square root of 2, or the square root of 7. These have never-ending, non-repeating decimals. So again, these are never-ending, non-repeating decimals. So if you plug these into your calculator to get a number, you'll get really messy, gross numbers that there's no rhyme or reason, or there's no pattern to their decimals. So that's why they're irrational. They don't really make sense. They're never-ending, non-repeating. So that's really all we're going to say about irrational numbers. But then we're going to jump over to rational numbers and categorize these. So within rational numbers, you can further break them up into other groups or make more narrow categories of numbers. So the next set of categories numbers we're going to talk about is integers. So integers include all positive and negative whole numbers, including 0. So this could be anything from -2, -1, 0, 1, 2, and so on in both directions. So you can go more negative or more positive, but really any number that you would typically see on a standard written out number line. So it goes from -infinity to infinity, as long as they are whole numbers and include 0. Within that, we're going to further narrow our categories or make even more exclusive groups. So each group gets progressively more exclusive or starts separating itself from other numbers. We have whole numbers. And these include 0, but it goes 0, 1, 2, 3, and so on. So in this case, we're no longer including the negative numbers. So when we get to whole numbers, we've now dropped all the negatives, and we're just working with the positives. The most narrow and exclusive category we're going to mention is natural numbers. And this takes out 0, but it's otherwise the same. So the only difference between whole numbers and natural numbers is whole numbers include 0, natural numbers does not. So those are the different sets of real numbers. So those are the terms you should know when speaking about the specific sets of real numbers. But that's all we're going to talk about for those for now. The next thing I want to talk about is placing numbers on a number line. So we're going to do an example of that for graphing numbers. So the example I'm going to jump into is, what is the graph of the numbers -5/2, 5, square root of 2, and 2.6 repeating. So what we're going to do is graph these on a number line. So the first step is going to be to put all these numbers in comparable or similar forms. So just by looking at these, it's hard to know which one's greater or less than, though you can see that one's negative. So it's going to be helpful, I believe, to put them all into decimal form. So you might already know, but -5 divided by 2, if you can put it in your calculator, or if you just know it, is -2.5. So now I know that's -2.5. If I plug the square root of 2 into my calculator, I'm going to get approximately 1.4. So again, make sure you use the approximately equals, not the actual equals, because as we previously mentioned, square root of 2 is an irrational number, so it really is a never-ending non-repeating decimal. But for the sake of this problem, we will round it to the nearest tenth. And last but not least, we have 2.6 repeating, which is already in decimal form, so I don't need to do anything with that. So the next step I'm going to do is draw my number line, or draw your graph. So I'm going to draw it here. And looking at my numbers, I know I'm going from -2.5 to 2.6 repeating, so I'm going to round down on both and up on each side. So I'm going to start with -3, then do -2, -1, 0, 1, 2, 3. And now I'm going to place these in the appropriate spots, but then label them with the original, in the original form they were given. So my third step is going to place on graph and label with original form, or in original form. So in this case, I have -2.5, so I know that's going to be between -2 and -3. So I place it exactly halfway between and label that -5/2, since that's the original form it was given in. Next, I'm going to do the square root of 2, which I know is 1.4, so it's going to be between 1 and 2, but a little bit closer to 1. So we'll say right about there. And I'm going to label that square root of 2, since that was its original form. Last but not least, 2.6 repeating between 2 and 3, a bit closer to 3. So I will label that 2.6 repeating. And I am done that problem. Great. Last thing I want to do is, or not last thing, sorry, we have one more bit of chunk of information, but let's do a quick check together. So I want you to do the same thing we previously did. What is the graph of square root of 3, -1.4 repeating, and 1/3? So pause this, try this on your own real quick. I'm going to go over it now, so if you haven't stopped, stop it. So again, let's put these in comparable form. I have the square root of 3 is approximately equal to 1.7. -1.4 is already in decimal form. And then 1/3 is equal to 0.3 repeating. So I'm going to draw my number line. And I can see that these are going to be between, this is -1.4, so -2, and that's going to be closest to 2. So -2, -1, 0, 1, 2. Now I'm going to place them in the appropriate spot. So I know 1.7 is between 1 and 2, a bit closer to 2. So I'll put the dot there and then put the square root of 3. So that's the original form. -1.4 I know is between -1 and -2, a little bit closer to -1. So I'll put that there. And last but not least, 1/3 is a third of the way between 0 and 1. So I will label that as such. Great. So that is my solution. That is my graph for those three numbers. Make sure you write down any questions you have about that process. And I'm going to turn the page to go over our properties of real numbers and their definitions. So the last thing we're going to talk about is the properties of real numbers. And these are a lot of things you've worked with before, but we'll review them again really quickly. So first, I want to know in these definitions, let A, B, and C be real numbers. So obviously these are properties of real numbers. So when we're talking about numbers or using variables to represent numbers, we're talking about real numbers, not imaginary. So we're going to make a little table with the property here. and then the addition version of that property, and then the multiplication version. So here's our table. First one is closure. So the closure property, and that just says a plus b is a real number for addition. So basically, if you add two real numbers, you're still going to have a real number. And same with multiplying. If you multiply two real numbers, you'll still have a real number. Sorry, a real number. Just saying, they're not going to suddenly become imaginary when you add or multiply them. The commutative property says that a plus b is the same as b plus a. So it doesn't matter what order you add those two real numbers, you'll still have the same sum. And similarly with multiplication, a times b is still equal to b times a. It doesn't matter which order you multiply them, you will still get the same value. The associative property says if you have three numbers, so we'll say a plus b plus c, if you group a and b, it will not change the value if you do that or group b and c. So if you group a and b and then add c, it's the same as adding b and c and then adding a. It's still going to be the same total sum. And similarly, if you multiply a and b and then multiply by c, it's the same as multiplying b and c and then multiplying by a. So when you're multiplying or adding, it doesn't matter which order you're doing that. As long as you're only adding or only multiplying, it's going to give you the same value regardless. Next, we have the identity property, which just says that a plus 0 is equal to a, or 0 plus a is equal to a. Doesn't matter. Similar to the commutative property, doesn't matter which order you add that. So the key vocabulary here is 0. I'm going to put a line through this so you know it's 0. 0 is the additive identity. So if you add 0 to any number, you will keep that number. Similarly, if you multiply any number by 1, you will keep that number the same. So a times 1 is still a, or 1 times a is still a. So in this case, 1 is the additive, or the multiplicative, sorry, we're talking multiplication now. Multiplicative identity. Great. Two more real quick. So we have inverse. So this just says that a plus negative a is equal to 0. Or similarly for multiplication, a times 1 over a is equal to 1. So again, to get to the additive identity of 0, you would just add the negative version of that number. To get to the multiplicative identity of 1, you would just multiply by 1 over that number. All this is saying is this is how you cancel a number out. You would subtract or you would divide if you're multiplying, depends on what you're doing. These are things you have probably done before, just not necessarily put the specific vocabulary to. Last but not least, we have the distributive property, and this kind of cuts across both addition and multiplication, because this says that a times b plus c is equal to a times b plus a times c. So as you may have seen before, you can distribute in and get that value. All right, one quick check and then we're done. So which property does the equation illustrate? So which one? Question mark. So if I have negative 2 over 3 times negative 3 over 2, and I get 1, which of the properties in the table above is that demonstrating? Pause, try to answer on your own. All right, so the answer you should get is the inverse property of multiplication. So if you look up here, you can see that these are canceling each other. So this is 1 over this number, or this number flipped, it's reciprocal. We can talk more about exactly what I mean by that in class, but basically this says that since I flipped this number, it's the same as putting 1 over this number. They cancel each other out, and you are left with just 1. All right, make sure you write down any questions, comments, concerns so we can go over them together in class.